Welcome to AI Peer Review, the show where we take some of the most cutting-edge, and let's be honest, sometimes dense research in machine learning and really try to distill it down.
Today, we are definitely digging into one of those. It's a paper that I think tackles one of the most frustrating architectural challenges in self-supervised learning right now.
We're talking about Joint Embedding Predictive Architectures, or GPAs. And this new paper is called LeJEPA, Provable and Scalable Self-Supervised Learning Without the Heuristics.
Yeah, and that title is perfect. It just gets right to the point.
It does, because GPAs are, they're a fantastic blueprint, right? You train a network to predict the embedding of one view of some data based on another view. It sounds so elegant.
It does. But the reality of implementing it is just, it's a mess of Band-Aids.
A total mess.
Yeah, and that mess is what everyone calls representation collapse. Without, some really careful intervention, the network learns the laziest possible shortcut.
It just maps every single input, no matter what it is, to the same point in the embedding space.
Exactly. Total collapse. And to stop that, researchers end up with this heavy toolbox of ad hoc tricks. Stop gradients, these huge teacher-student networks, really complex schedulers for your hyperparameters. It's just a ton of R&D.
So LeJEPA, which stands for Latent Euclidean JEPA, basically comes in and says, hey, stop playing whack-a-mole.
Right. Let's solve this from first principles.
And the goal is to make it lean, scalable, and really theoretically grounded. They want to boil this entire collapse problem down to just managing one single hyperparameter, this lambda.
Precisely. So our mission for this deep dive is to really understand how they pulled off this theoretical purification. We need to unpack two huge ideas.
Okay.
First, why is the isotropic Gaussian distribution the provably optimal shape for these embeddings? And second, how does their new objective, CGREG, actually enforce that geometry at massive scale?
All right, let's start with the theory then. The whole goal of a foundation model is to build this organized, useful embedding space.
Yeah.
Right. An affida that works for tasks as a model is never even seen.
But the authors here make a very specific claim. For this to work, the embeddings have to follow an isotropic Gaussian distribution.
Which is a bold claim. Why that specific shape? Why not something else?
It all comes down to minimizing risk. Specifically, the worst-case risk across all potential downstream tasks.
Yeah.
If you're building a general-purpose model, you need it to be as flexible as possible.
And they prove this using linear probing.
Yep, the standard evaluation technique.
So you freeze the trained encoder, you pop a simple linear classifier on top, and you see how well separated the features are.
Exactly. And when you do that, using something like ordinary least squares, your estimator has bias and it has variance. And what this paper shows is that the actual geometry of your embedding distribution is what's driving the instability.
So if the geometry is wrong, if the features are sort of stretched out or squashed in weird ways, what they call anisotropic, how does that actually hurt performance?
It just makes everything fragile. They've got two really powerful proofs in the paper. The first one looks at when you use standard regularization on your linear probe, like Tikhonov regularization.
Okay.
The proof shows that anisotropy, those squashed axes in your feature space, it actively amplifies the estimation bias. You're basically biasing your own solution without meaning to.
Wow, so the very thing we use to keep the probe stable, the regularization, ends up working against us if the geometry is bad to begin with. That feels very counterintuitive.
It is, but it gets worse. The second proof shows that even if you use no regularization, that same anisotropy still amplifies the total variance of your estimator.
So you're stuck. Either way, a lopsided anisotropic embedding space is just fundamentally high risk.
It's unstable. You get much higher variance in your final probe parameters.
Yeah.
So the isotropic Gaussian is the Goldilocks solution. It's the unique geometry that minimizes that risk across the board. And this even extends to nonlinear methods like KAN.
Which basically reframes the whole engineering problem. You stop trying to just prevent collapse somehow, and you start trying to enforce this perfect Gaussian geometry exactly.
The theory sets the goal. But now, of course, you have the engineering challenge. How on earth do you enforce a high-dimensional, isotropic Gaussian shape on, say, 1 billion samples running across hundreds of GPUs?
Yeah, your first thought might be traditional distribution matching, but those just become computational nightmares at that kind of scale.
A complete nightmare. The problem is the complexity. A lot of these methods are what we call ON2, so the compute scales with the square of your batch size. That is a total non-starter for massive training runs.
So they needed a shortcut, elegant one.
And they found it in this idea of sketching.
This is based on the hyperspherical Kramer-Wald lemma, right?
Yeah.
Which is a really key piece of theory here.
It's beautiful. It's so simple. The lemma basically says that matching a full high-dimensional distribution is the same, mathematically, as matching all of its one-dimensional projections.
Okay, break that down.
So instead of trying to compare your entire, say, 512-dimensional embedding space to a 512D Gaussian.
Which sounds impossible.
Right. Instead, SIGREG just takes a handful of random directional vectors. You can think of them like taking random slices through the data, and it just makes sure that the data projected onto those 1D slices looks like a simple 1D Gaussian.
Okay, so that simplifies the problem from 512 dimensions down to a bunch of 1D comparisons. But you still have to actually test those 1D slices. You need a statistical test that works, but also one that scales.
And they looked at all the usual suspects and threw them out. Moment-based tests like Jarque-Bera, they fail because higher-order moments can give you unbounded exploding gradients. That'll crash your training run for sure.
They also rejected CDF-based tests, like Kramer-von Mises. Why was that? Those seem pretty standard.
The problem there is that they require sorting the data points. Sorting is not a differentiable operation. Plus, trying to sort data efficiently across hundreds of distributed machines is, well, it's not fun. It just tanks your performance.
So that brings us to the winner, the Epps-Pulley test. It uses something called the empirical characteristic function, or ECF. Why does this one solve all the problems?
The ECF is just a simple average of complex exponentials. That operation is naturally differentiable, it's very stable, and this is the critical part, you can compute it across all your GPUs with a single, efficient, all-reduce operation.
And the paper guarantees that this Epps-Pulley loss gives you uniformly bounded loss, gradient, and curvature, no matter what your input distribution looks like.
Bounded gradients. That is the holy grail for training stability. It means the model can't just run away and collapse to some extreme, unstable solution. And by using that sketching idea, the whole thing maintains linear complexity, 1 n to rel, which makes it perfect for training huge models.
There's a cool nuance there, too. You might worry about the curse of dimensionality. Like if you have a 512-dimensional space, do you need 512 slices to check it properly?
That's a great question. And empirically, they showed that you don't. Even for really high dimensions, using a pretty small number of slices, like 16, is enough.
How does that work?
Because of how SGD works. The iterative nature of the training and the smoothness of the embedding functions mean that over time, those random slices end up covering and correcting all the degenerate parts of the space.
So this all comes together in LeJEPA's final loss function. It's just the standard prediction loss plus this SIGREG loss, all balanced by that one lambda hyperparameter.
And this is where all that theoretical rigor really starts to pay off in practice.
You get to throw out all the complexity.
Exactly. Since SIGREG prevents collapse by its very nature, you don't need stop gradients. You don't strictly need a teacher-student network. They even show you can get rid of register tokens, which is another little hack people use to keep things stable. The elegance is just in how little you need.
And it's not just simple, it's robust. They validated this thing across more than 50 different architectures. ResNets, VKs, ConvNext.
And even on some gigantic 1.8 billion parameter models. And the stability isn't just about architecture. It holds up across a huge range of batch sizes and values for lambda, so you can spend less time tuning and more time actually modeling.
Okay, but here is where, for me, it gets really interesting. It starts to challenge the whole paradigm in the field. For years, the story has been train on a massive generic data set like ImageNet, and then you transfer that knowledge.
Right, the transfer learning playbook. LeJEPA really questions that.
How so?
They ran these experiments where they compared LeJEPA, trained from scratch on small, very specialized data sets like Galaxy 10 for astronomy or Food 101 for food images, against these huge frontier transfer models like Deno V2.
Models trained on just massive amounts of general web images.
Exactly. And the results were kind of shocking. LeJEPA, when trained in domain on that small specialized data, it actually outperformed the massive transfer models.
Wow.
This is a huge finding for anyone working in a specialized field. It proves that if you have your own niche data, building a custom LeJEPA model on a sound SSL objective can be a much better strategy than just defaulting to a giant generic model.
That completely reframes the economics of pre-training. You don't necessarily need a multi-million-dollar GPU budget to build a really effective specialized model.
As long as your SSL objective is mathematically sound, yeah. And this geometric constraint, it doesn't destroy the meaning in the data, it just organizes it better. The visualizations in the paper are amazing. You can see clear object background separation emerging with no supervision at all.
Okay, let's talk about one more major practical benefit. A pain point that every single SSL researcher has felt for the last decade.
Ah, yes. Model selection.
The agony of it.
Yeah.
You're training a model for days, your loss is going down, and you have absolutely no idea if the model is actually getting any better.
The training loss is usually meaningless. It tells you nothing about final performance on a real task. So you're forced to run these expensive supervised linear probes constantly just to check your work. It's so slow and costly.
So does LeJEPA fix this broken signal?
It does. This is a critical breakthrough because the objective is so rigorously tied to this optimal geometry. The actual LeJEPA training loss has a high correlation with the downstream linear probe performance.
How high are we talking?
It's already strong with the raw loss, but they found this simple mathematical scaling law you can apply. And once you apply that, they were able to push the Spearman correlation to nearly 99%.
99%. That means for basically the first time in many of these setups, you can just watch the training loss curve and know you're picking the best model. That saves a huge amount of time and compute.
This whole paper is just such a great story of deriving real, practical simplicity from deep theoretical rigor. They solved the core geometric problem of JEPA with a scalable objective that ends up being like less than 50 lines of PyTorch code.
It really shows that if you get the fundamental math right, a lot of the downstream engineering problems, they'd sort of melt away.
They really do. Enforcing that optimal geometry, that isotropic Gaussian, is what fundamentally resolves all the historical instability of these architectures.
Which leaves us with a final provocative thought for you to take away. The objective in LeJEPA is provably optimal for minimizing the worst-case risk across all possible downstream tasks.
Right. It's built for maximum generality.
But what if you weren't building for maximum generality? Imagine you had some high-confidence knowledge about the future. You know your model will only ever be used for, say, a specific family of generative tasks, and never for classification. How would you need to change this objective? If you could incorporate that partial knowledge about the kinds of tasks your embeddings will face, could you engineer a geometry that's even more optimal for that specific niche?
That really is the next frontier, isn't it? Moving beyond perfect generality and toward informed, domain-specific geometric optimization.
We'll leave that thought hanging there in the embedding space. Thank you for joining us for this AI peer review deep dive.